Hello, this is my investigating reinforcement learning presentation for SIT215, Artificial and Computational Intelligence. As an introduction to this presentation, I'll be giving an overview of how a random policy implemented to an OpenAI GIMS taxi problem compares against an actual training algorithm called Q-learning or quality learning, which can learn and apply its knowledge to better itself through each iteration of the program that it's being run on. I'll also be supporting these statements with secondary game, in which I'll be comparing the same parameters and the same algorithms, but in a different environment to contrast the difference. So in the secondary game, I will be comparing a randomness algorithm as well as the Q-learning algorithm to the second game, the same two algorithms to the first game, and just comparing how they are different to two separate games. An introduction to Q-learning. Before we can dive straight into the results, we need a basic understanding of what Q-learning is and how the Bellman equation works. Q-learning is an off-policy algorithm which can interact with the environment in two different ways. The first is to refer to a Q table, which is a matrix that stores every single game state possible and the corresponding Q value for that game state. However, not always do we have the best options in our Q table, as each time the algorithm is ran, the Q table is going to fill up. And this is where the concept of exploration comes in. This is our second option with Q-learning. Epsilon is the randomness factor that decides how often we're going to ignore the current value we have in the Q table, and we're going to go out and pick a random value, as this random value could have a potential to be better than the currently discovered one in the Q table. So this factor is usually 0.1 or can be much higher or much less, depending on how easily you want the values to be changed, how easily modifiable you would like them to be. If you've already got a pretty solid Q table set up, this value might be extremely small, but just always giving it that little bit of room to improve your values. It's only going to take the new value of randomness if it's better than the previous one. The problem we're going to be looking at is the taxi problem. This problem is a major reinforcement learning problem, which includes a taxi, some walls, a person to pick up, and a place to drop them off. The reason this works so well is there can be a calculated number of states that can all be predicted ahead of time to work out the best possible path. This is why we're training. We're sending through 10,000 episodes of this game. Not even that many for this game because it's a relatively small game, and the Q table is only going to have around 500 cells in it. Based on the x and y, the n by n square of this, every single state can be predicted. So at every single state this taxi's in, we are 100% going to know what move it needs to make to get down to the person and drop them off in the least possible time. So the results of the random policy that I implemented to the taxi problem, as you can probably expect, an algorithm that's completely random cannot perform too well. In saying that, it actually did not at all. The random policy took 391 different moves to reach the goal. The goal is to pick up the person and drop them off without touching any of the poles, without doing anything bad. If we start averaging it out over many episodes, we can see that over 100 episodes, the average number of time steps taken was a lot more than 391. It was 2,239.23 steps per episode. That means that for every single move this makes is a single step. It's taking 2,239 steps to eventually get to this person and come up here and drop them off, to choose the right action to pick up the person and to choose the right action to get up there to drop off. There's a massive difference there. We must remember that this is truly based off randomness. There's no patterns or learning involved. One episode can be completed in 5 moves and another could complete it in 3,000. Now, on the other side, we have the results from the Q-learning. After the application of the Q-learning algorithm and the adjustment of the hyperparameters, we were able to conclude that after running 100 episodes again, however with the Q-learning algorithm in place this time, the algorithm managed to average 12.92 time steps per episode. The algorithm is deemed perfect for over 100 episodes if it's averaging a fault average of 0.0, meaning that it's completing the problem without losing a single reward. So to compare the results and the randomness to the Q-learning algorithm, after running and training both of them, it's extremely clear to see that there's no noticeable difference between the two. There is a noticeable difference between the two, sorry. Firstly, the random policy algorithm is returning an average of 2,239.23 time steps over 100 episodes of the taxi problem. Let's compare this to the implemented Q-learning algorithm, which had a return of 12.92 average time steps over 100 episodes and with a fault average of 0.0, meaning that that is the lowest time each one could have. This illustrates that for 100 episodes, an applied Q-learning algorithm would improve over the performance of a random algorithm by 198%, meaning that there's a 198% increase in the number of steps taken from the random algorithm to the Q-learning algorithm. Here's a graphical representation of these results that I've just been talking about. These are the training graphs for the Q-learning algorithm. The Q-learning algorithms on the left and the random policies on the right. They may look similar, but if we take a look at the y-axis here, we can see that the highest range for the Q-learning algorithm is 18, meaning that 18 steps, and the lowest is 8. So the lowest time that it was completed in was 8 steps and the highest was 18. Even though they both look very jittery and very jumpy, if we jump over to the right-hand side graph, which is the random graph, we can see that the upper bound is 10,000 steps and the lower bound is 0, meaning that the fluctuations here are much larger, and that's to put it into scale of how much the randomness means, how much the randomness is different compared to the Q-learning. So the second game we're going to be looking at is the cart pole problem. Cart pole, also referred to as an inverted pendulum, is a game in which a pole is attached to an unactuated joint to a cart that moves along a frictionless track. The objective is to keep the pole balanced by applying forces of +1 or -1 to the pivot point. So if we just take a look at this game, the cart is going to be you have the option to move the cart left or right. That's how small the action space is for this game. It's either a left or a right. This stick is the pole on top of it is going to be initialized with a certain angle, making it fall one way. So the job of the algorithm is to determine which way the pole's falling and counter-correct that by moving the cart the other way to balance it. If the cart moves any more than 2.4 units in either direction, then the game is considered to be lost, or if the pole falls more than 15 degrees downwards, the game is considered to be lost as well. So applying the same algorithms that I've just mentioned before to this game, we can see that the graphs represented below are representing evidence of the outcomes generated in a Q-learning algorithm. The left graph is the Q-learning one. So this is the graph that has the implemented Q-learning algorithm. So you can see it starts off very consistently small, nowhere above 75. The time steps in here are every single time that the cart is moved. So every time step is it's almost like a single second. If you think of it like that pace, 1, 2, 3 is a time step, and every single time step you can move the cart. That's how this game's measured in, how long the pole lasts on top, how many time steps that pole lasts on top of the cart for. So if we take a look over here, each up until about 100 episodes, it was lasting 75 time steps. Once we start getting up past 100 episodes plus, when the Q-learning algorithm really starts kicking in and starts learning, we can see that it starts jumping up and averaging upwards of around 175 until eventually it reaches 200, which is the max that we've let it have. So once it starts getting up there, it hits 200, it starts jumping down and correcting itself again until roughly anything more than 150 just plateaus at a 200 rate because the algorithm has perfected itself. If we move over to the randomness algorithm in this case, these are really good to compare against each other because we can see that this one's only up to 100, and even then it's not touching it. So it's completely random. We're seeing on the 20th episode that we're coming up and touching almost the 100 mark. Not 80th episode, we're touching almost close to it as well. But then on the 140th, we're literally back down to almost 0. This is just showing that there is 0 pattern in the randomness algorithm. It's just completely random and it's picking random actions at each time. However, for this game, it looks a lot better because there is only 2 action spaces, moving left or right. So it's a lot easier for the algorithm to choose the right one, if that makes sense. It's a 50-50 chance that if the correct one, if it needs to move right, 50-50 chance that this algorithm is going to pick right. And that's why these values are so high. So to compare both the games and algorithms, there was one major difference in applying the algorithm to both games. The algorithms did not simply just slot right in, especially for the cart pole game. The cart pole game has a notion of infinite values involved in it. The way the game works is through trigonometry, and in which some of the variables are between infinite values, making it hard to create a Q table for an infinite amount of values. So with this game, the angle of the pole, the pole velocity. The pole velocity is measured from negative infinity to positive infinity. And like I said before, with the taxi problem, we try and create a Q table that has states, has every single possible game state. And we can't do this for the cart pole problem, because creating a Q table that ranges from negative infinity to positive infinity is basically impossible. So as a result of that, we had to discretize some of the values using bucketing. This is basically just saying creating ranges for the values that turn values into categories instead of values. So we don't have to write out every single value from negative infinity to positive infinity to always know the right state. We can chop these down to a lot smaller cases. And that was how we overcame that major hurdle in implementing the algorithm to the cart pole problem. This obviously wasn't the case in the taxi problem, where we could just calculate every single state of the game, because everything was true, either is or it isn't, and there was only 500 states of the game, and it was easy just to calculate the corresponding Q value for a state. Other than these issues in terms of training and implementation of the algorithms, both games behave very similar, and both the games responded very, very similar in getting trained. That's all. Thank you.